Alright, we did bronze, let's get into the silver. Very epic stuff. Hello everybody, I'm Carr, and today we are going to be doing the 2021 January contest, USACO Silver. So why don't we just jump into it? I don't really have much else to say, let's do it. We're going to do it in C++, by the way, because C++ is very epic. Alright, dance moves. Farmer John's cows are showing off their new dance moves. I love the fact that they spelled it with moves, that's so cool. At first, all N cows are standing in a line with cow I in the I position, seems legit. The sequence of dance moves is given by K, pair the positions, okay. And in each minute, the cows in positions AI and BI in line swap, okay. So basically it repeats indefinitely, okay. Seems legit. Please determine the number of unique positions in the line she will ever occupy. I think this is like basically swappity swap if you guys remember that one. I think we won't have to do much different from that one. Okay, so it includes N and K, and you basically have to print N lines of output. Alright. Well, okay, so basically the idea is like what? Huh. Okay, wait, let's just write this out in our scratch paper. So you basically have to start with like 1, 2, 3, 4, 5, right? And then originally 1 and 3 swaps, so you get 3, 2, 1, 4, 5. Then 1 and 2 swaps, so now you get 2, 3, 1, 4, 5, right? And then 2 and 3 swaps, so these two, so you get 2, 1, 3, 4, 5. And then 2 and 4 swaps, so 2, 4, 2, 4, what? 3, 1, 5. Okay, there we go. Okay, so basically like eventually this thing will repeat, right? Okay, so let's just look at 1, right? So 1 goes to here, right? And now it's in the 4th position, so in the next like loop of it, it'll go to the 2nd position, because 4 moves from 4 to 2, and now it's in the 2nd, and then it'll move back to 1. So then it'll take 3 cycles to get 1 back to its original position, right? It'll go here, 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 okay? And basically, in the process, it will go through how many different locations, right? So within one cycle, it goes 1, 3, 3, 2, 4, right? So it already go through 4 different things, right? And then when it's in the 4th position, it'll go through whatever the 4 went through in one cycle, and then it'll go through whatever 2 went through in that cycle. So what is K? K is, okay, so 10 to the 5, alright. So essentially we could only go through it once, and then we had to somehow figure out how many things it goes through. Huh, well the thing is we can't do like, for each like number we keep track of which positions it's gone to. We can only keep track of like a count of it, not like the actual positions, because that would be way too big. Because that would be like 10 to the 5 squared, so we can't just directly keep track of it. We gotta keep track of the actual number. Huh. So how do we know so how many unique positions cow I reaches? So can we like find how many positions it doesn't reach? Is that possible? Okay, so let's think a little bit. So 2 goes to these 2 spots, 3 goes like that, right? Then 1 goes like that, 5 is always at the end, 4 goes like that. But the thing is, you can't keep track of which ones you've gone to, because that would be n squared memory, which is too much. So what do we do? Okay, I guess we could kind of draw it like a tree, right? So, could we draw it like a tree? So, let's see. So, essentially, like, what? Could we draw it like a tree? I don't think we could really easily draw it like a tree, right? Okay, so I think I have an idea, right? So essentially, in one cycle, right, we basically see that like 1 goes to here, then it goes back here, then it goes here, right? So essentially, it already has 4 unique things, and now it's in the 4th spot. So now we have to see like what the 4th does, but whether it overlaps at all. But that's annoying. Okay, so a swap only moves 2 things. Does that matter? Let's see. So if it only moves 2 things, then only 2 things will automatically go to places they haven't gone to, right? But then after the first one, then we don't have that guarantee. Okay, let's draw this out. Okay, so let's make this a little bit more spread out. So 1, 2, 3, 4, 5, then 3, 2, 1, 4, 5. I'll just write it out. Okay, so this goes here, this goes there, then this goes there, this goes there. These all go straight down if they're not swapped, right? Then what's 3 and 1 get swapped and everything else moves down. This moves down, this goes there, and this moves down. Alright. Okay, well I guess basically the thing that's cool is that you can maximum have 2k moves, right? Because each swap only moves 2 things, right? So, if it only moves 2k moves, then if we only keep track of what? Well, yeah, okay, so if we keep track of a list of how many things each thing has gone through, then we could max have like 2k numbers in our list, so that should be fine. Okay, so what happens if we just keep track of how many things, if we just keep track of which positions they go through, right? So one, or let's just erase all that, let's go back to this. Okay, so one goes through, or let's see, where do I write this? Why don't we zoom out a bit or something? Okay, why don't we move over a bit? Alright, so one goes to positions, what? 1, 3, 2, 5. Or we could just use a set, like an unordered set, so it'll do 1, 2, 1, 2, 3, 4. Okay, so those are the 4 positions for 1. 2 goes through, like, what? 2, comma 1. 3 goes 2, 3, 1, 2. And 4 goes from 4 to 2. And then 5 goes from just 5. It's just 5. Okay. So, if we have this, then essentially 1 ends up at 4, right? So then essentially 4 goes to 4 and 2, so we basically like union with that, right? We add in these to that, and then you union these to that. But that could potentially be like n time though for each one, so how do you do it smartly? Oh wait, so there are cycles. Okay, I see. So basically like, how does this work? So 4 goes to, so wait, what? So 1 goes to 4, right? So 1 goes to 4, 4 goes to 2, and 2 goes to 1, and then these two don't even move. So these two don't move, okay. Oh, so that's why 1, 2, and 4 all have the same number. Oh, wait, that's so big brain. Okay. Oh, ha. Alright, now that makes a bit more sense. Okay. Oh, that makes so much more sense. God dang it. Okay, I see. Alright. So essentially what we gotta do is we basically gotta break it up into cycles, right? So we have this one cycle, which is 1, 2, 4. We have another cycle, which is just 3. And we have another cycle that's just 5, right? Then essentially, every time we like go through it, we have like our cycle 1 is going to be 1, 2, 4. We'll have 1, 3, and 5, right? Okay, now everything that 1 goes through, 4 has to go through, right? Because it'll eventually get to 1 and then come back to its original. So everything that 1 goes through, 4 is also going to go through. Everything that 1 goes through, 2 is also going to go through. And everything that 2 and 4 go through, 1 is also going to go through, right? So essentially, we just go through it, right? So 1 and 3 are swapped. Okay, so 1 goes to 3. So we add, like, okay, so this has 1, 2, and 4 already because all of these are already in the cycle. This already has 3. This already has 5. So essentially, 1 is going to go to 3, right? Because our first one is swap with 3. So this is going to be plus 3. And then 3 is obviously going to go to 1. So we do 1. Alright, so that took 2 times for the first swap. That's like 2. So if we do this throughout all k, it's going to be 2 times k, which is fine. Then we go to the next one, which is 1, 2. So now we basically look at what's in 2 and what's in 1. So 3 is going to move to 2, and 2 is going to move to 1. So 2 is in this group, so we add 1, but 1 is already there, and it's a set, so we should be good. And then we go on to the next one, which is 2, 3. So 2 and 3. So 3 is moving to 3, but we already have that. Then 1 is moving to 2. We already have that, so that's fine. Then 2, 4. So that's going to be 2 and 4. So 4 is moving to 2, and 1 is moving to 4, but those are already in the set, so that's fine. So now we do 1 is in this set, right? So that's size 4. So our first answer is 4. 2 is in this set, so the size is 4 again. 3, the size is 3, so we print out 3. 4 is the first set again, so that's 4. And then 5 is 1. And we get the answer. Yes, okay, that's how you do it. That makes a bit more sense. Alright, let's do it. Alright, we do C++. What is this going to be called? Moves. I love moves. Okay. Bro, why do they have to be so good at puns, dude? It's not fair. Alright, using namespace std int n comma k, and we'll have our, how should we do this? Should we have swaps? Let's use pairs, because pairs are cool. Pair, type def actually. Alright, now we could say, pii, what? There could be 2 times 10 to the 5, so we'll just do like 10 to the 6 or something. Swaps. And then we just read everything in like cool kids. So, c is nk, or int I equals 0, I less than k, I plus plus, and then we see in swaps I dot first, swaps I dot second. Okay, so now the first step is to figure out how many cycles there are, right? So we just apply all the swaps, and then we apply the swaps and we see where things go, right? So we'll have like what should we say? Well, it's gonna be an int array, and we'll call it like swap. How about that? And that only has to be 100,001. Why not? You know, why don't we be cool and make this 2,000, 2 times, like, you know, like that. There. That's a bit big. There. And now we're just gonna get the swapped array. So essentially, we're gonna do what? Well, we also need a set of. Oh yeah, we first need to do that, and then we can do that. Okay. So for like what? Int I equals 0, I less than k. Oh, we can just apply it directly, right? Okay. So essentially, we're gonna start with for int I equals 0, I less than n, I plus plus. Why don't we do one index because that's cool. Swapped I equals I. Okay. And then here we're just gonna say int temp is equal to swapped, like swaps I dot first. And then we're gonna do swapped I dot first is equal to swaps I dot second. And then swapped, this is so annoying, we just copied this, is equal to temp. Okay, so that swaps it, right? And then at the very end, we should have a swapped array, and now we can find our cycles. Okay, so we're just going to go through it, I equals 0, I less than n, I plus plus, and then we're going to keep track of which cycle each guy is in. Okay, so our first cycle is going to be, let's say, what? Well, this is fine. Wait, no, cycle has to be, okay, so this has to be 1001 because each thing, we have to keep track of which cycle it's in. So we'll keep track of our current cycle, so int car cycle, and then we'll set every car cycle to like -1, or cycle I is equal to -1. Okay, so if like cycle I is like greater than, or is, not equal to -1, then we're gonna like continue because we already looked at that. Otherwise, we're gonna set cycle, or actually, okay, so we'll say int car is equal to I, and then while car, or we could do this, so cycle I is equal to car cycle, and then car is equal to swapped I, and then while car is not equal to I, then we're basically gonna do cycle car is equal to car cycle, and then we're gonna like do car is equal to swapped car. Okay. So essentially, all the guys who are in a cycle with 1 will be set to cycle 0. All the guys in a cycle with 2 will be set to cycle 0 because they're in the same cycle. 3 will be set to 1, and then 5 will be set to 2, ideally. And then at the end of this, we should just do car cycle plus plus. Okay, so let's just print it out so we're not trolling. See out cycle. Try this. Well, that did not work. Hold up. What's swapped? Swapped I. Let's see. Okay, let's try that. 0, 2. Wait, what? Oh. 1 less than equal to n. We gotta remember that we are 0 indexing this boy. Okay, that makes a bit more sense. Okay, so how do we get 0 though? What? Again, we're doing this wrong. Okay. Okay, there we go. So now 1, 2, and 4 are in the same cycle. 3 and 5 are in different cycles. Okay, very good. And I should go to the bathroom real quick. Probably should have gone to the bathroom before doing this, but it is okay. Alright, nice. We made it successfully back from the bathroom. Very cool. Okay, so our cycling is working. Now we basically had to do our cool, like, set thing. So now we basically need a array of sets. So we'll do set int, I don't know, visited, I guess. Yeah, visited, why not? And then we should probably include set. Okay, so essentially what we're going to do is we're going to go through each one, each of these swaps. So we're going to go 0 to k, and then we're going to keep track of, what should we do? Well, first we got to keep track of, okay, so here we should just do like, visited car cycle, dot add, or what is it, insert? Yeah, okay, insert. And we are going to insert I, okay? And then we're also going to insert everybody else who gets added after, so we're going to do car, insert car. So now we basically go through all of our swaps, and we basically add it to the set if it goes to a new location. Well, we don't even care if it goes to a new location, so once again, we have to start from the beginning, right? We need to start with no swaps done. Okay, yeah, so we basically just do this again, except we don't want to reset our cycles because we already did that. And then we want to take this, essentially. Except this time, when we swap it, we basically want to, like, keep track of what? So, well, basically, what? We want to do, like, okay, so visited of the cycle of the thing that is getting moved. So that is going to be swapped, like this thing. So that's what's getting moved. And then we want to insert where it's getting moved to, which is swapped I.second. And then basically you want to do that for the other way too, so the second getting moved to the first. And then we do that. Okay. And we probably just do this underneath for sake of keeping things together. Alright. And then at the very end we just go for int I equals 0, I is less than equal to n, or I is 1, I is less than equal to n, I plus plus, and we want to see out, what? We want to see out visited cycle I dot what? Dot size. Okay. Hey, it works, first try. I mean, we'll see about that, but I think it should be fine. Alright, let's do this. Plus work. Let's go. Will it work or will it fail? That is a question. Alright, it works. Nice. Very epic. Okay, moving on to the next one. Oh, what? Okay, well, what? I'm gonna time out. There's no way to time out, right? It should be fine. Okay, very epic. Alright, now we go on to No Time to Paint. Alrighty, Bessie has recently received a painting set. Let's make this bigger. And she wants to paint the long fence at one end of her pasture. The fence consists of n consecutive 1 meter segments. Alright, she has 26 different colors, and she labels them letters A through Z in increasing order of darkness. Okay. She can therefore describe the desired color she wants to paint as an length and string. Okay, and initially they're all uncolored. All right. So she can color any contiguous range of segments with a single color and a single brush stroke. Okay. But she can't paint a lighter color over a darker color. Wait, that makes things pretty good, right? Because that means we know that the darker colors always have to, no, sorry, the lighter colors always have to go first. Yeah, so basically you would have, okay, that makes sense, that's good. For example, an initially uncolored segment of length 4 can be colored as follows. You basically have to put the earlier letters first and then later letters, right? Okay. Running short on time, she thinks she might have to leave some consecutive range of fence segments unpainted. Okay. She's considering Q candidate ranges, okay, and for each one, what is the minimum number of strokes needed to paint the fence? Okay. Alright, so you basically have N and Q. You got your string, and you have your Q's. Okay. And how big is this? So N is 10 to the 5, so that's pretty big. How big is Q, though? Q is also 10 to the 5, so essentially you had to do it pretty fast. Okay, so basically, well, how we could think about it is like, okay, so we know that A has to go first, right? So essentially we know that like, if what? We know that A goes from like the 0th index to the fourth index. So if the only reason we would have to paint with 2 strokes to do the A's is if the Q breaks up that like length of A's, right? Instead of doing 1 stroke, you'd have to do 2. If the Q doesn't actually break it up, like if it like cuts off this A, right, and it doesn't split it into 2 separate A's, then it doesn't change how many strokes we have to do. So basically by default, like you take 3 strokes, right? Actually, how many by default do you have to do? You have to do 1 stroke for the A, 1 stroke for the B, two strokes for the B, and then 1 stroke for the C. So by default you have to do four strokes, right? And then if you split up one of the A's, so if you do 3 to 6, then 3 to 6, what's that? Well, that just cuts off like that. So it doesn't like cut any stroke. So wait, does it? So 3 to 6. 3, 4, 5, 6. So essentially it doesn't, so it should just be 4, right? But then 1 to 4, 1 to 4, 1 to 4, that basically gets rid of this entire B stroke. So in that case, you subtract 1. Alright. So essentially there's like 2 cases, right? Either it splits up an existing stroke into two strokes, right? Or it completely like overrules a stroke, right? Okay, so basically if it ever like completely encloses a stroke, then it's going to delete that stroke. If it ever like is completely within a stroke, it's going to split the stroke. So we basically have to find the number of strokes it does for each of those, and then we should be good. So how do we do that? How do you do that fast? Okay, so first we could like pretty quickly find like how many strokes are like where each stroke starts and ends, right? So essentially A is just from the first A to the last A, B is until you hit an A, right? So this is 1 stroke, and then this is the rest of it. And then C is just until you hit a B, so that's another one. Okay. So if you have all the strokes, then how do you quickly find whether a stroke is completely covered? So, okay, let's see how many strokes you're completely within, right? So essentially you have like, let's see. So essentially you have like a stroke, right? You have like a bunch of random strokes. Oh, well, okay, well, that's interesting. That's interesting. Strokes have to completely enclose each other, right? There's no way you can have like a stroke like this. That doesn't make sense, because then this stroke might as well just end here. Oh, so they are mutually exclusive or they include each other. Wait, that is kind of epic. Okay, that's good. So let's say our Q starts here and ends here. Then, like, we could pretty quickly. Okay, so we first see let's see how many strokes is enclosed by, right? So we find the left thing here, right? And then we find out how many like things are on the right here. But essentially we need this thing to not, wait. Oh, so we only care about this one. Could anything like to the left of this guy also be overlap, go over? Yeah, it could. Well, huh. So basically anything here could basically go over, right? Well, I guess if you keep track of how many like strokes are underneath this like one right here. Okay, well maybe this one ends here though, and then this one ends on the other side, right? That's also possible. Huh. So how do you quickly find it though? Whether it is completely enclosed. Oh. Okay, so we basically see how many ending ones there are inside, right? One of it ends for one that starts inside though, right? Okay, I just need to figure out how many ways are there, like how do you find quickly how many like sets are within a certain like boundary? How many like segments are completely within it? Oh wait, there's 26 letters, does that help? Then essentially, like uh if you have a stroke, well could you have like, okay, so let's say like we know there's a C here and there's a C there, and then there's like B, B, and like A. Does that matter? Like, is there any? Okay, so you can have like a C that starts here, ends here, and then a C that starts here, ends there. But then, yeah, then you can have like an A that starts there, ends there, ends there. Huh? What? How do you do this? Let's see. There gotta be a smart way to do it, right? Wait, could you just go through each letter, right? You could just say like, is there an A that goes over this bound? Oh, yeah, I could. Wait, wait a minute. Wait, I think you could, right? Because essentially, like, you know that like the A's are all like there are no overlapping A's. It doesn't make sense to have like an A within an A. That doesn't make any sense. There are no overlapping ones, right? So essentially, you just like binary search. You find the closest A here, and then check if it ends on the other side. Then you know that A goes over here. And then similarly, you could just like do like the closest one. You could do if A was like within it, right? You could do the closest one to the right of it, and then see if it's within it. Okay, well that works. Okay. I think we got it. I think we got it. All right. So basically, step one is to figure out what strokes there are, right? So essentially, you start with A, and you basically say the first A is here, the last A is there, and that's basically your answer. So um, so yeah, you basically say A is from 1 to 5, B is from 2 to 3, and like whatever that is to the end, and then C is just that. And then you could apply my logic in order to find whether it's completely overlapped. And if it completely overlaps, then you subtract one. If it completely encloses it, then you add one. No, sorry, the other way around. If it completely encloses one of the strokes, then you subtract one. Okay, that makes sense. All right, this might be annoying to code though. God dang it. Okay, well, what is this called? Let's see. Paint. Painting. Why not? This is so sad. There's no cow memes here. All right. Int n and q, and then we basically got our string s, let's say, and then what else do we got? We got our ranges. So we'll do another type def nonsense. Okay, pii in our pii, what do we call it? Q ranges. Yeah, sure, why not? Range 100,000. All right, so cin n and q, then we cin our s, then we for int I equals 0, I is less than q, I plus plus, and then we just do c in range I dot first, range I dot second. Okay, so we read everything in. Now we basically just got to go through it and figure out. So we'll do strokes. So it'll be a list of pair I. So vector pii strokes, and that'll be like 26 long. Then you probably include vector, and we should probably have something to convert from letter to a zero indexed array. So we'll basically have like, whoa, no, what are we gonna do it? We'll do it down here. Int cur to num char c, and literally all we gotta do is we do return c minus capital H. Okay, so now in order to figure out like strokes, right, we basically just go through it, and if we ever see something smaller, then we had to break your current stroke, right? So say we got like for int I equals 0, I less than 26, I equals plus. For int j equals 0, j is less than 20, or n, j equals plus. And essentially we'll have like a start, we'll do int start is equal to -1, and okay, and then int end is equal to what? It'll equal -1, I guess. So if s j and then put a num of that is equal to I, then we basically have to do stuff with it. Or we'll say is less than I. Then we want to set start. Whoops. All right. Then we want to set start is equal to -1, right? Because we want to start. Well, we had to end our previous thing. Then, or well, we should probably like do. Okay, if start is not equal to -1, then we want to do strokes I dot pushback start comma end. All right, and we just set start equals -1 and is equal to -1. Otherwise, if per num sj is equal to I, then if start is equal to -1, then we basically want to set start is equal to j and end is equal to j. Otherwise, we want to just say end is equal to j. Okay. And then if at the very end, if this is the case, then we just want to do insert the last one in there. Okay. All right. So let's just check that. Well, we could pretty easily check that all the strokes are right. So we'll just do for I equals 0, I is less than 3, I plus plus, for like PII, P in what strokes I, we'll do C out, I, then space, then P dot first, then space, then P dot second. Alright. Alright, let's try that. Alright, so 0, yeah, okay, so it goes from 0 to 4, that's what we thought. Then it has 2 strokes, 1 to 2 and 5 to 7 for B, and then 6 to 6 for C. Alright, so we have our strokes down, very cool. Now we basically just like go through it, go through each of the Q, and we check if it fits totally within one or totally outside of another. Okay, so, oh, we need default number of strokes. Okay, so default number of strokes we got to keep track of. Strokes equals 0, or whoops, we already have that. Int total tot is equal to 0. Then we'll probably do like over here, we do tot plus equals 1 plus plus. Okay, so now we have our total number of strokes, right? And then essentially, we'll go through our Q's for int I equals 0, I equals Q, I equals plus. Then essentially, we want to check like for each of the letters. So for int j equals 0, j is less than 26, j equals plus. And then essentially, we want a lower bound within the vector. So, how do we do this? So we want a lower bound and we want an upper bound. Okay, so first let's do lower bound. So we'll do like iterator vector int itr, or no, other way around, is equal to lower bound, or we could say lb here, just to make it clear that it's lower bound. Lower bound, what? Strokes I, or strokes j dot begin, comma strokes j dot end, and we want to find q, or sorry, what do we call it? Range I dot for, wait, range I, yeah. Oh, parent int, right? Okay, there we go. And then why don't we just see out the pair? So we'll do like star lb dot first. Wait, what? Oh, do I need to do like that? Okay, and then star lb dot second, and go. Okay. Okay, 0 0. What? Exited segmentation faults? What? Oh, yeah, okay, I see. Let's just do, like, what? If the vector size is bigger than 1, then we should do that. Alright, so essentially for 0, we got 0 comma 0 to that. What? Why? Okay, why don't we just see what the values are? Oh, I guess we should do minus minus because there's a 0 indexing here. Alright, so this makes a bit more sense, but where the heck are they getting 0 0 from though? That's not even a thing, right? Lower bound, you get the 0th index. What? Okay, hold up. Let's just copy and paste this over here. So for int or PII P in strokes J, P out P or J space P dot first. Okay, so 0 4 1 2 5 7 6 6. How did it get 0 0 though? Oh, because it gets it like above. Oh, I see. Okay, yeah, that makes sense. So it is doing it right. Well, okay, let's think. So it is like above that. So it basically sorts, or should it be upper bound? Okay, so if it's like equal, right, then you want to do upper bound and then you can subtract 1, right? Because you always want to subtract 1. Okay, so we're going to do upper bound and subtract 1. Or can we do lower bound and plus 1? And then if the, like, LB is less than strokes J dot size, that means that it is within the array. So then we basically say if, like, strokes J LB dot first is within it, right? So greater than or equal to, well, it should be greater than or equal to, right? Oh yeah, let's do that. I think we should do range I dot first, and then it should also sort before anything that's equal to it. So we should do range, or the 0 here, so that it sorts before everything. It's greater than or equal to range I dot first and strokes. Okay, we should have like int car over here. Int car is equal to tot, and then if this is true, strokes J LB dot second is less than or equal to range I dot second. Then we do, so that means it's completely within the range. That means we would do tot plus plus, or no, car plus plus. Okay. Okay, why don't we make a new pair I sorter is equal to range I dot first, comma 0. Okay. And now we'll just put sorter in here. Okay, and then we just do the same thing for upper bound, right? So this should be something that will sort last in the thing. So it'll be like, yeah, so we could just do like a really big number for the sorter. So sorter, and then this is like really big. Okay, and then we do upper bound. Wait, what? No upper bound? Seriously? Wait, hold up. There is upper bound. What? Did it? Oh, I probably should do that. Okay, include algorithm. Okay, and if it is less than, then we basically just do if upper bound is the other way. So first is less than or equal to, and the second one is strictly less than because we want it to be or like that. Okay. Then we do car minus minus. Wait, what? Car. Okay, so this is if the range completely encompasses it. So it'll be car minus minus, and then this will be car plus. Okay. And then at the very end, you want to do cout car. Oh wait, what? That's not the very end, right? Oh. Whoops, UB here. Okay. Bruh. Why am I doing I there? Okay. J should be all there, and that should be better. Okay, so let us just cout like strokes J LB dot first space strokes J LB dot second. Alright. And we can get rid of this. I'll just comment it out for now. Actually, we already know that that's working, so that's fine. 1 4? Where did I find 1 4? What? Hold up. Oh, that. Wait, what? Question mark. Where do you get 1 4 though? What? Okay, 0 0 4. Okay. Oh, that was from the top. Okay. So, yeah. So basically, the first one is 3 6, and then it looks at 5 7, and then 5 7 is not completely within, right? It checks if it is also within it, but it's not. Wait, why is it looking at 5 7 though? JLB dot second is less than, or then it looks here. Okay, so this is right for this one, right? No. So this one is supposed to, what? Oh, it should be -1 here. -1. Okay, good. But why is it subtracting 1? So strokes LB dot first is greater than or equal to range? No. Okay. So less than or equal to? Oh, so if we get well, why is top so small? Top plus e plus plus, right? Oh, over here too, right there. Okay. All right, finally, dude. That took a while. God dang it. Okay, now we can get rid of all our print statements. I don't want to print that out. All right, nice. Okay, let's try it. It's probably not gonna work because it's a very thick implementation, but hopefully it does. We'll see. Nope. God dang it. What do we do wrong now? The sorting thing is kind of sus. I will admit, bruh. Okay, why don't we just try our own case, right? So, why don't you just cut off this entire end part? Then it should be 5, or it should be 2, because you're only going to do the A and the B, so that should be what? I don't know. We could do 5 to 7. 5 to 7. Let's see. So we gotta do this 5 to 8. Okay. Okay, that works. Maybe we could do like 5 5 or something. Okay, that's right. It should not impact it at all. What else could we do? Huh, why don't we make it go up? Let's see. So we could do like 5 1 or something, and then 5 A's, and then what, like 2 3, which is 2. That works. Okay. What about like 5 1 A B C B A, and then we get rid of the C in the middle with 3 3 3 3, right? Oh, it is 4 though. 4 is right. Bruh, wait. Huh? Bruh. Wait, there could be multiple things like within the thing. Okay. That would make a lot more sense. Okay. So, essentially, we can't just do this. We basically got to figure out how many things are within it. So, we basically got to do like, so basically how many sets there are from this starting point to that ending point. Okay. Bruh. Alright, so then we had to upper bound the ending point. No, lower bound the ending point. So we want how many ending points are less than or equal to it. Upper bound, so less than or equal to is upper bound. Upper bound minus 1. Okay, so we gotta do the other thing. How do we do this? Okay, so we'll basically take this over here. Well, we'll basically make another upper bound. Oh, that's so sad. Okay, I see. Okay. So basically the point is you can have like 3 little tiny ones within the same one, in which case you get rid of like 3 strokes in one go. So, in this case we want to do like range I, or range QI, yeah, okay. And we want to do a special comparator, so okay, so basically we gotta make our own comparator, so we basically do like bool compare second, and we'll take PIIA, PIIB, and we just return A dot first is less than B dot second. Whoops. Alright, so in this case, we want to just do lower bound on that. So, or no, we want upper bound. So we want stuff that ends there. Okay, and then we'll give it the compare second. What do? We basically do car minus equals UB minus LB. Okay. So basically the case is, oops, what's the thing? Alrighty. Whoops, that's not what I want to put in. We want to put like, let's do 10, 1, and then A, D, A, D, A, D, A. Is that 5? One more. Okay. So essentially if we go over all of these D's, we want the answer just be 2, right? So we could go 3, 2, 4, 5, 6, 7. 3 to 7. What? Bruh, hold up. Oh, we don't want to subtract a 1. Okay, 3. Why are they doing 3? So, oh, this is like number that ends before it, so we want to do plus 1 then, I guess. No, that's not right. But then you have lower bound, which basically gives you the first one that is above it, and then this is the last one that's within it too. Okay, that should be right. Really? Okay, let's see. 10, 1, A, D, A, D, A, D, A. So that is going to be 7, 8, 9, 10. So 3 to 7. So it should subtract, when it gets to D, it should get like, one of them is 3, 3, one of them is 7, 7, and it'll subtract, it'll get like upper bound of the third one, so that'll be 4. So it'll do 4 minus 0. Or wait, what? It'll get 3. It'll get 3 as its upper bound. Let's see out upper bound and see what happens. So for D, it should get 3 as the upper bound. Whoops. Okay, so it got 3 as the upper bound, which is as desired. So then what do we get as the lower bound then? Okay, lower bound it got 0, so it's subtracting 3, and then it is adding 1. Wait, what? Then what is car? So 4 minus 3 should give a, so car. So it starts at 4, that is correct, and then it subtracts 3. So it goes 4 minus 3, and then it adds 1 for the A, right? Okay, let's just see out car at the end. Oh, I have so many see out cars. Let's see. And then we want to see out like, oh, this should be fun. Let's see this. 6? How to get a 6, dude? Bruh. Okay, so after the first one, it literally got a 6. So the first A is going to have like that and that. Upper bound is going to be 1. Lower bound is going to be 0, right? Okay, so upper bound, wait, so the ceiling, okay, so the lower bound is 1. So 3, 7. How is it? Oh, lower bound. Okay, yeah, it is 1. Oh, but it ends after, so it will be 0. Oh, okay, so basically you just have to do like if upper bound is less than lower bound, or upper bound is greater than or equal to lower bound, then we do that. Because otherwise that means that it started before and ends after. In which case we could probably just use this to, else we could do car minus minus, right? And just get rid of all this nonsense, right? See if this still works. Okay, so that still works. And then how does our new one still work? 10, 1, A, D, A, D, A, D, A, D, A, 7. Okay, so, oh, else if, wait. Okay, maybe we shouldn't do that. Let's just do this like that, okay. Alright. Oh, finally, okay, so that's working. That should be fine. Let's test this. Yes. Yay, we did it. Okay, finally. That took a while. God dang it. I hate debugging like lower bounds and upper bounds, but it is okay. I'm sure there's a little bit of a cleaner way to do it, but we got the idea originally. We just needed to be faster at executing it. It is okay. Alright, let's see if we can finally finish spaced out quickly. Farmer John wants to take a picture of his cows grazing in their pasture to hang on his wall. Nice. Alright. The pasture is represented on an n by n grid of square cells. Okay. With 2 is less than or equal to n is less than or equal to 1000. In the last picture Farmer John took, his cows were too clumped together in one region of the pasture. This time around, he wants to make sure his cows are properly spaced out across the pasture. He therefore insists that no 2 cows may be placed in the same cell. Every subcell must contain, every subgrid of 2 by 2 must contain exactly 2 cows, so that's valid. And that's not true because the bottom right does not, okay. So we want some cells to contain more cows than other cells. So, alright. So you want to get the total, maximum total beauty. Okay. Alright, so the first line contains n, the next n lines, okay, so you basically got this is the value. And eventually you just want to have 2 in every 2 by 2 grid. Okay. So how big is n? N is 1000. Okay. So you can do n squared. Okay, so you basically go through it only once. Okay, so basically for every 2 by 2 square, there's basically like 16 possibilities, right? You got, or wait, what? For every 2 by 2 square, there's like 4 choose 2. There's 6 possibilities, right? So for every 6 possibilities, we could keep track of like how many cows, right? Okay, so basically we could just, let's see if we just like go like right and then go like this down it. So for the first one, we try to get the maximum value. We put those 2 on the top ones. Then we move on to the next one. And then you can basically like go through all the possibilities of the previous one, right? You go through all the possibility of this one, right? And then this one's only impacted by the top one. This one is only impacted by this guy and this guy, I guess. And this guy is only impacted by this guy and this guy. So if every single thing must contain 2 cows, then you basically have like what? Well, basically the idea is you only care about your top left cows, right? So essentially like you could loop through all 36 possibilities for filling up these, or all like what, 2 to the 7 possibilities for, well, not even 2 to the 7, there's probably less than that. But basically all the possibilities for filling up your top left 2 squares, and then you just like figure out like what the maximum value of doing that is. So why don't we break it up into like these 2, right? Then this top guy, well, they're not independent still though, so that's annoying. Okay, so let's say we have the values for every single possible like configuration of this dude, right? Then we go to this guy, and for each configuration, we try a configuration that's valid for this guy, and then add it to however, whatever the like configuration for this guy was. But then this way might be different too. Wait, so when you decide this guy, right? Or like if you decide this guy, then this guy basically has like no options, right? Like if there is one C here, then the 2 C's could there's 2 options, right? If this is a C and this is a C, there's no options. Both of these have to be dots. If like neither of these guys are C's, then both of these guys have to be C's. So there's basically like maximum 2 options for this guy, for the next guy after you set this one. Okay, why don't we just decide the top row then, right? Then basically the bottom row is almost, uniquely determined, right? Because if these two, this one is a C, then essentially this guy has to be C or this guy has to be a C, right? Well, okay, let's say there's two C's here, then no C there, then there's only one option, right? Then there's C here, there's C there, then, or there's only a C here, and all of these are blank. Then, like, this has to be a C, well, this has to be a C. Wait, both of these have to be C's, right? And then this guy can't, or this guy has to be a C too. Huh. So if the top one is determined, does that mean that the next one is also determined? Okay, so let's say there's C, no C, no C, or C, no C, C, no C. Well, then there's two options. You could either have it here and here, or you could have it here and here. Okay, so why don't we just do it in order? So let's say there's a C, like the maximum of this is a C is 0. The maximum of this is a C is 6, right? The maximum of this is a C is 7, because you could technically do all 7. Oh, okay. The max of this is a C is 8, okay. Then max of if this is a C, given the top thing. Well, it depends on this one and this one. Why don't we like go this way? So this one is max, like, this is a C, then this one could be a C. Wait, no, but then it depends on that too. Oh yeah, so for each 2x2 thing, we store the maximum if that one was set to configuration whatever, right? Then, if we do this one, then this one, then this one. How do you do this? This is kind of hard, huh? Okay, why don't we do like, okay, CC, right? Then we do like C, C, dot, 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 dot. Is there anybody to make this work? No. Okay, so let's say we have two things in a row here, right? Then, what do we know? Okay, so then we basically know that, let's see, and we know those two. Okay, so, well, we need, oh, okay, I see. So we know this is fixed, right? That means that one of these, huh. Okay, so let's see. If we have like CC, then we know that it has to be dot dot CC dot dot, right? And then is there any way to make this like, well then in this one we can either have C nothing or nothing C, and then same thing here. But if there's C nothing, then we know that this has to be C nothing too. Wait, so if we do like two in a row, that means they have to be alternating like every other for the other dimension, right? Huh. Oh, wait, is that useful? Well, yeah, because then we could choose one dimension in which to alternate every other, and then we could just like fill it in, right? Because let's just say, okay, so if we know that it's alternating in one dimension, then we know that like any alternation will work, right? So you could do dot C dot dot, like it'll always work as long as you're alternating in any dimension. Okay. Well, oh, so then we just look at both dimensions and then we just see which alternation is best for each column, and then we can add it up. Oh, wait, that's so big brain. Okay, let's do that. Alright, that makes so much more sense. Bruh. Alright, so we'll have using namespace std int n, int matrix 1001 by 1001, cnn for int I equals 0, I less than n, I plus plus. Then we basically have like, and then we just, we have to do for int j equals 0, j less than n, j plus plus, cn matrix I, j. Okay, so now we just have sums for each column and sums for each row. So int row sum and int col sum, and we basically just go through it. Okay, so we go through each row. Or wait, we could just do this over here. So if j mod 2 is equal to 0, in which case it's an even, then we add it to the current row. So we just do, or row sum, oh, so we could just do like, okay, yeah, so we'll do 2, and then we just do like row sum I plus equals, or row sum I j mod 2 plus equals matrix ij, and then call sum I mod 2, or I mod, no, j I mod 2 plus equals matrix ij. And then essentially we just go through each call sum and we take the bigger of the two, right? So we just go int max row sum is equal to 0 into max call sum equal to 0. I is less than n I plus plus, what do we do? Max row sum plus equals max of row sum I 0 and row sum I 1. And we do the same thing for max call sum. And then we just see out the max of these two, max row sum, max call sum. And we should be good. Okay. Hey, very nice. Okay. So let's submit this boy. Alright, we're almost done. Come on. Let's do it. Hey, finally, we did it. Very nice. Alright, we did it. Very nice. That is all I got for you guys today. Thank you guys so much for watching. As always, if you enjoyed the video, leave a like and subscribe for more. Let me know what else you guys want to see. But other than that, I'm done for today. So, thank you guys for watching and see you guys next time.